Hello viewers, welcome to online course on Mathematics 3. This course basically for undergraduate student or BTech student of engineering field. Today we are going to discuss about the cyclic group, and this part is on the algebraic structure. Myself Sanjay Vishwas, Assistant Professor of Mathematics, Department of Applied Science and Humanities of Guru Nanak Institute of Technology. Here is my details of contact information. If you have facing any kind of problem regarding my online class, you can call me or send message through my mail ID sanjay.vishwas@gnit.ac.in. So before we start today's lecture, let's quickly recall in the last lecture. So in the last lecture we have discussed about the subgroup. In this lecture we have discussed about the definition of a subgroup, and you know that subgroup is basically it is a group also, and it satisfies all the properties of a group, and it is a subset of a set G. So in that case, where H be a subset of G and H is said to be a group if it satisfies all the properties of a group. And after that we have talked about some related theorem on subgroup, and then we have discussed about the examples of subgroup. So today we will discuss about the cyclic group, and it is my fourth lecture on algebraic structure of Mathematics 3. So here is the content of today's lecture. So at first we will define the cyclic group, that means the introduction of a cyclic group, and after that we will discuss some related theorem on cyclic groups, and then we will talk about some illustrative examples on cyclic groups. So mainly in this chapter we will discuss about the definition and some theorem and some illustrative examples on cyclic group. And the cyclic group is the very important part on the group theory as well the algebraic structure. So first of all, we are begun with the definition of cyclic group. So here is the definition. So a group G composition is called cyclic if there exists an element A in G such that every element of G can be expressed as A to the power n. So you know G composition is a group, and it satisfies all the properties of a group theory, that means closure, associative, identity and inverse property. And this group is called a cyclic group if there exists an element. So G is a non-empty set, so there is at least one element in G, and say it is A, and A is in G such that every element of G can be expressed as A to the power n, where n be any integer. And this integer is either positive, negative or 0. Then the element is called the generator of the cyclic group. Thus if A is the generator of the cyclic group G, then G is equal to A to the power n such that n belongs to Z, which is denoted by G is equal to within less than and greater than A or within second bracket, and this is called the generator of the cyclic group G composition. So generator means if there is a point in a cyclic group G composition and order of any element of a group G is equals to the order of a group, then this element is called the generator of a group. Okay, so this is called a generator. So there may be more than one generator of a cyclic group. So in a cyclic group there exists at least one generator. Okay, and this generator, that means the order of this generator is equals to the order of a group. So for example, the multiplication group G, and G is equal to there are four elements 1 minus 1 I and minus I, and it is a cyclic group. As we can write, G is equal to I square, I to the power 3 and I to the power 4. So I be an element, and I square is equal to minus 1, and I to the power 3 is equal to minus I, and I to the power 4 is equal to 1. So I be the element, and whose power, that means I square, I to the power 4 and I to the power 1, and it is equals to 1 minus 1 I and minus I. That means the order of an element I is equal to 4. That means I to the power 4 is equal to 1, and 1 is the identity element of the multiplicative group. So order of the element I is 4, where 4 is the least positive integer such that I to the power 4 is equal to identity, and the group whose order is also 4. So therefore I is a generator of the cyclic group G composition, while composition is a multiplication. As well as we can write G is equal to minus I whole to the power 2, minus I whole to the power 3, minus I whole to the power 4. So power of I to the power 2, I to the power 3 and I to the power 4 as well as minus I, and after simplifying this we will get it G. Okay, so that means 1 minus 1 I and minus I. So therefore in that case, where the order of minus I, it will be 4. So therefore minus I is a generator of G, and G is a cyclic group. So in that case, where I and minus I are two generators of a cyclic group G composition. Her composition is a multiplication, and G is the set, and G is the finite set whose elements are 1 minus 1 I and minus I. And after that we will take one more examples on the cyclic group. The group of integer Z plus, and it is a cyclic group with generator 1, because any positive integer m of Z can be expressed as 1 plus 1 plus 1 and up to m times, that means 1 to the power m. And any negative integer minus m can be expressed as minus 1 plus minus 1 plus minus 1 and up to m times, that means 1 to the power minus m. And 0 can be expressed as 0 is equal to 1 to the power 0. So this is the cyclic group. Let us move on the next slide. So in this slide we will discuss about some related theorem on cyclic groups. So here is the theorem. This is the first theorem on the cyclic group. Every cyclic group is an abelian. This is a very important theorem on the cyclic group. So here is the proof. Let G composition be a cyclic group generated by A. So A be the generator of a cyclic group G composition. Okay, so A to the power n is equal to E. Okay, where n be any positive, negative or 0. Also let x comma y is belongs to G, and then there exists integer a r and is such that from the cyclic group x is equal to a to the power r and y is equal to a to the power s, where a is the generator and xy is belongs to G. Xy be two elements in G, and r comma s are two integers. So from the definition of a cyclic group, which implies x is equal to a to the power r and y is equal to a to the power s. So from this we will prove that it is abelian, that means G composition be an abelian. So now x composition y, so it is equals to, where x is equal to a to the power r and y is equal to a to the power s. So x composition y, it is equals to a to the power r composition a to the power s, and this is equals to, you know that, a to the power r plus s, and a to the power r plus s can be written as a to the power s plus r, and that means a to the power s composition a to the power r. And you know that a to the power s is equal to y and a to the power r is equal to x. So x composition y, it is equals to y composition x. So therefore x composition y is equal to y composition x for all xy belongs to G. So therefore G is abelian. But the converse part of the above theorem is not true. So for example, let us consider the set G. Okay, and G, there are four elements E, A, B, C, and this one, that means composition is a binary operation and defined on G by E composition A is equal to A composition E is equal to A, but E is the identity element and ABB and ABC are the non-identity elements. Similarly, E composition B is equal to B composition E is equal to B, E composition C is equal to C composition E is equal to C. As well, E composition E is equal to A composition A is equal to B composition B is equal to C composition C is equal to E. So therefore, order of A, order of B and order of C are all equals to 2. And A composition B is equal to B composition A is equal to C, A composition C is equal to C composition A is equal to B, and B composition C is equal to C composition B is equal to A. So this is the relation between the all elements with the binary operation. So therefore, the composition table is given by this is the composition table where the first row it is the elements, so E, A, B, C, and first column it will be the elements as well E, A, B, C, and there is a composition. Okay, E composition E is equal to E, E composition A is equal to A. So okay, I have already mentioned in the previous slide as well. A composition A is equal to E, B composition B is equal to E, C composition C is equal to E, A composition B is equal to C, A composition C is equal to B. Okay, as well. So therefore, from the above table, it follows that G composition is an abelian group of order 4, but it is not a cyclic group. So you know that in a cyclic group there exists at least one element whose order is equals to the order of a group. But in that case where the order of a group is 4, that means in that case where G has an element E, A, B and C, that means order of a group is 4, but there does not exist any element whose order is equals to 4. So in that case where order of A is equal to 2, order of B is equal to 2 as well as order of C is equal to 2. So G composition is an abelian group of order 4, but there exists no element whose order is equals to the order of a group. So there is no generator of G composition. That means G composition is not a cyclic group. So the converse part is not true. And the above group G composition is known as Klenes 4 group and is denoted by K4. Okay. So after that we will discuss about the second theorem on cyclic group. So this is the second theorem. If A is a generator of a cyclic group G, then A inverse is also a generator. Okay, this is the second theorem. So here is the proof of the second theorem. Let X is belongs to G, then there exists an integer R such that X is equal to A to the power R, where A is the generator of a cyclic group G. So now X is equal to A to the power R and it can be written as A to the power minus 1 whole to the power minus R. And you know that the n, that means A to the power n, where n is either positive or negative or 0. So we can take minus R is equal to P. So therefore A to the power R, this is equals to A to the power minus 1 whole to the power minus R. It can be written as A to the power minus 1 whole to the power P. So where P is equal to minus R is an integer. So hence A to the power minus 1 is also a generator of a cyclic group G composition. So hence the proof of the above theorem. So A be the generator of a cyclic group, then A inverse is also the generator. So if G is equal to generator of A be an infinite cyclic group, then G has exactly two generators, A and A inverse. Okay, so if G is an infinite cyclic group, then there exist two generators and they are A and A inverse. Okay, the note on the above theorem. So after that we will take the one more theorem on the cyclic group. This is the theorem number 3. Let G composition be a finite cyclic group generated by A, then order of G is equal to n if and only order of A is equal to n. So here is the proof of the above theorem. Let order of A is equal to n. So we shall prove that order of G is equal to n, where G composition be a finite cyclic group and generated by A. So then order A to the power n is equal to E by the definition of a order. We have A to the power n is equal to E. So then E is the identity element of G, and A to the power s is not equals to E for 0 less than s less than n. So if s is less than n, then A to the power s is not equals to identity. But when if s greater than n, then by division algorithm there exist two integers q and r, where q is the quotient and r is the remainder, such that s is equal to nq plus r, where r is rising 0 to n and r is strictly less than n, not equals to n. If r is equal to n, then n is divisible by s. Okay, so therefore a to the power s, and it is equals to a to the power nq plus r. So that means s can be written as this nq plus r. So therefore a to the power nq plus r, and it can be written as a to the power n whole to the power q into a to the power r. And you know that the order of a is equal to n, that means a to the power n is equal to e, where e is the identity element. So this equation is implies a to the power s, and it is equals to e to the power q into a to the power r, and the power of any identity element is equals to the identity element. You know that. So a to the power s is equal to a to the power r. Thus there are only n distinct elements, a square, a to the power 3 and up to a to the power n in G. Hence order of a is equal to n. And next let order of a is equal to n, and suppose order of a is equal to m, then by the previous argument order of G is equal to m. Hence n is equal to m. So therefore order of a is equal to n. Hence the proof of the above theorem of the cyclic group. And this is actually if order of G is equal to n, then order of a is equal to n, as well as if order of a is equal to n, then order of G is equal to n. This is the theorem, or the third theorem of a cyclic group. And after that we will take the another theorem, that means the theorem number 4, and it will be a finite group G composition is cyclic if and only if there exists an element A is belongs to G such that order of A is equal to order of G. So here is the proof. Let G composition be a cyclic group generated by A. Then by the above theorem, that means the theorem 3, we have order of A is equal to order of G. I have already proved this theorem. Next, let us assume G be a finite group of order n, and G has an element A such that order of A is equal to order of G. That means order of A is equal to n, then a to the power 1, a to the power 2, and up to a to the power n minus 1 to n a to the power n, where a to the power n is equal to E. E is the identity element, you know that. Our distinct element is G, and hence G is equal to within second bracket, that means a to the power 1, a to the power 2, a to the power 3, and up to a to the power n. And this is the generator of A. So thus G is a cyclic group. Hence the proof of the fourth theorem of cyclic group. Let us move on the next theorem. So this is the fifth theorem on the cyclic group. Let G is equal to generator A be a cyclic group of order n. So A is the generator of order n. Then for any integer r where 1 less or equal to r less than n, a to the power r is a generator of G if and only if r and n are prime. That means relatively prime. This is the fifth theorem. So let r be relatively prime to n, and also let H is equal to generator of a to the power R and be a cyclic subgroup of G. So obviously H is a subset of G, and we can write it equation number 1. So G is a cyclic group generated by A of order n, and H be the another subgroup, cyclic subgroup of G, and which is generated by A to the power R. So obviously H is a subset of G, and this is equation number 1. So since R is relative to prime to n, so there exist two integers u and v such that ur plus vn is equal to 1. By the number theory, we have ur plus vn is equal to 1. So therefore, a to the power 1, so a to the power 1 can be written as a to the power ur plus vn, that means a to the power ur into a to the power vn. And a to the power ur can be written as a to the power r whole to the power u, and a to the power vn can be written as a to the power n whole to the power v. And you know that A will be the generator of a cyclic group G of order n, so a to the power n is equal to e. Therefore, a to the power n whole to the power v is equal to e to the power v, and e to the power v is equal to v. You know that the power of any identity element is identity. A to the power 1 can be written as a to the power r whole to the power u, and it is belongs to H. You know that, and which implies G is a subset of H. So from 1 and 2, that means combining the two equation 1 and 2, we get H is equal to G. That means a to the power R is a generator of G. So next, let G is equal to a to the power R. That means the generator of a to the power R. That means a to the power R is the generator of G. Then we will show that R and N are relatively prime. So from this, let the greatest common divisor of R and N be D, and D is not equals to 1. That means D is greater than 1. Then R by D and N by D must be positive integer, where D is the greatest common divisor. That means, and D is not equals to 1, so R by D and N by D both are the positive integers. Okay, therefore e to the power R whole to the power n by D and is equals to a to the power n whole to the power r by d. So this term can be written as this. Okay, and a to the power n is equal to e, you know that. So A be the generator of a group G and of order n, so a to the power n is equal to e. So e to the power r by d and is equals to e. So obviously n by d is a positive integer less than n. Hence, order of a to the power r is less than n. And you know that n by d is a positive integer, and d is greater than 1, so n by d is always less than n. So hence, order of a to the power r and is equals to n by d, and n by d is less than n, so order of a to the power r is less than n. So therefore, a to the power r is not a generator of G. So, and which is a contradiction. I have already considered that a to the power r is a generator of G. So it is only when if d is equal to 1. So therefore r is a prime to n. That means r is not divisible by n. That is GCD of r comma n is equal to 1. So this is the proof of the above theorem. So there is a note on the above theorem. The first note, it will be the total number of generator of a cyclic group G of order n will be equal to the number of integers less than n and prime to n. Thus, if, so there is the example, G be a cyclic group of order 12 and generated by A, then all generators of G are, so the number is 5 to 12 and they are 1, 5, 7 and 11. So there are 4 numbers which are prime to n, that means 12. That means a to the power 5, a to the power 7 and a to the power 11 are the generator of the cyclic group G of order 12. And after that, we'll take one more note and or example on the above theorem. A cyclic group of prime order P generated by A has P minus 1 generators. So for all the generators are A square a to the power 3 and up to the power P minus 1. So for example, if G be a cyclic group of order 5 generated by A, then all the generators are A square a to the power 3 and a to the power 4. As well as if G be the cyclic group of order 7, then there are 6 generators and they are A square a cube a4 a to the power 5 and a to the power 6. That means 1 is prime to 7, 2 is prime to 7, 3 is prime to 7, 4 is prime to 7. That means prime to each other actually. 1, 2, 3, 4, 5, 6. These 6 terms and 6 values are prime to 7. That means a square, a cube, a4, a5, a6 are the generator of the cyclic group whose order is 7. Applying the above theorem, we will get this one. And a cyclic group having infinite number of elements has 2 generators. Now we will move on the next theorem, and this is the 6th theorem on the cyclic group. Every subgroup of a cyclic group is cyclic. This is the 6th theorem. So let H be a subgroup of a cyclic group G generated by A, where A be the generator of a cyclic group G. If H is equal to G or E, then obviously H is a cyclic group. This is the trivia. And so let H be a proper subgroup of G, then all the elements of H are integral power of A. Okay, so let if a to the power m is belongs to H, then a to the power m whole to the power inverse is also belongs to H, where H is a subgroup of G. So that means a to the power minus m is also belongs to H. So H contains elements which are positive as well as negative integral power of A. So this is the definition of the cyclic group, you know that. So any cyclic group can be written as a to the power n, where n be any positive or negative or 0. So n be the least positive integer such that a to the power n belongs to H, and it is the order of a group. So we shall show that H is equal to generator of a to the power n. So a to the power n is the generator of H. So let a to the power h, it is belongs to H. Then by the division algorithm, there exists an integer q and r such that, and here you know that a is greater than n. So n is the least positive integer such that a to the power n is equal to H. So we will consider a to the power s belongs to H. Then by the division algorithm, there exist two integers q and r, where q is the quotient and r is the remainder, such that s is equal to n q plus r, and r is lies in 0 to n, and r is strictly less than n. So now a to the power n, it is belongs to H, and this implies a to the power n whole to the power q, it is also belongs to H. That means a to the power nq is belongs to H, as well as a to the power nq whole to the power inverse. So you know H is a group and it is a subgroup of G, and it's also satisfy the inverse property. So if A is belongs to H, then A inverse is also belongs to H. So that means a to the power nq is belongs to H implies a to the power nq whole to the power minus 1 is belongs to H. That means a to the power minus of nq is belongs to H. So therefore a to the power s is belongs to H, a to the power minus nq is belongs to H. Then by the closure property of a group, a to the power s into a to the power minus nq is also belongs to H. That means a to the power s minus nq is belongs to H. And you know that from the division algorithm, s minus nq and it is equals to r. So a to the power r is belongs to H. So which is possible only when r is equal to 0, because n is the least positive integer such that a to the power n is belongs to H. So therefore s is equal to n, where r is equal to 0. That means a to the power s is equal to a to the power nq, and it can be written as a to the power n whole to the power q. Thus every element a to the power h belongs to h is of the form a to the power n or to the power q. So hence h is a cyclic group generated by a to the power n. This is the proof of the above theorem, that means sixth theorem on the cyclic group. After that we will move on the next slide. So in this slide we will discuss about the properties of a cyclic group. So the first property, the number of generator of a cyclic group is phi of n, where n is the order of a cyclic group and phi of n, that is equals to number of positive integer less than n and which is relatively prime to n. So for example, phi of 81, it is equals to phi of 3 to the power 4, and this is the properties of the phi function. Phi of 3 to the power 4, it can be written as 3 to the power 4 minus 3 to the power 3, and this is equals to 81 minus 27, that means 54. So the total number of generator of a cyclic group of order 81 is 54. Again, the phi of n, that means the number of generator of a cyclic group of order 7, and it will be phi 7, and it is equals to 7 to the power 1 minus 7 to the power 0, that is equals to 6. So the total number of generator of a cyclic group of order 7 is 6, and they are, a square, a cube, a4, a5, and a to the power 6. And this is the first properties of the cyclic group. So after that we will take the second property, and this one is the second property. For modulus of a is equal to n, so this is the order of a element a of a group G. Then generator of a to the power k, it is equals to generator of a to the power GCD of nk, and the order of a to the power k, and it is equals to n by GCD of n comma k. That means if the order of a is n, then the cyclic group generated by a to the k power is the same as the cyclic group generated by a to the power of the greatest common divisor of n and k. And also the order of a is the k power is equal to the order of a divided by the greatest common divisor of k and the order of a. So this is the second properties of the cyclic group. That means order of a to the power k, it is equals to n by GCD of nk. Okay. So there are some examples on the above theorem. So if in Z30 that a is equal to 1, then order of a is equal to 30. Since Z30 uses module addition, then a to the power 26 is the same as 26. What is the order of 26? So since GCD of 26, 30, it is equals to 2, you know that, and GCD of 2, 30, it is equals to 2. So it follows that order of 26 is equal to order of 2, and it is equals to GCD of 2, 30. Thus we expect that generator of 26 is equal to 2, and in fact this is 0, 2, 4, 6, 8 and up to 28, and 30 is equals to 0 as well. So we see that from the above properties, generator of 26, that means order of generator of 26, it is equals to order of generator of 2, and this is equals to 30 by GCD of 2, 30. That means 30 by 2, it is 50. Okay. And after that we will take one more properties of the cyclic group, and this is the third property. So for each positive divisor k of n, then the set, that means n by k generator, is a unique subgroup of Zn of order k, and moreover these are the only subgroup of Zn. So here is the list of the subgroup of Z30. They are generator of a, and it is equals to 0, 1, 2 and up to 21, and whose order is 30, as well as generator of 2, and it is equals to 0, 2, 4 and up to 28, and whose order is 15. The elements of generator of 3, they are 0, 3, 6 and up to 27, and whose order is 10. And after that we will take the generator 5, and the elements of generator 5, they are 0, 5, 10, 15, 20, 25, and whose order is 6. And generator of 6, and whose elements are 0, 6, 12, 18 and 24, and whose order is 5. And after that we will take 10, generator 10, and it will be 0, 10 and 20. The elements are 0, 10, 20, and whose order is 3. And the generator, it is 15, then there are two elements 0 and 15, and whose order is 2. And if we take 30, generator 30, and there is an element 0. Okay, 0 is the identity element in that case, whose order is 1. So these are the generators of the subgroup Zn, that means Z30. Okay, and the operation is plus in that case, and whose order are 30, 15, 10, etc., and up to 1. And after that we will take some examples on the cyclic group. So here is the example 1. So that the set G is equal to 1, 2, 3, 4, 5, 6. So G contains 4 elements, and they are 1, 2, 3 and up to 6. Form a cyclic group under the operation multiplication module 7. Find all generators of this group. So we have seen that the set G forms a group of order 6 under operation multiplication module 7, and it can be written as x cross 7. Okay, so we shall now show that the group G is cyclic. So for this we now find an element A belongs to G such that order of A is equal to 6. So G is a group, and G is a cyclic group if there exists at least one element whose order is equal to the order of a group. So we can, and you know that the group G composition where G contains 6 elements, that is order of G is equal to 6. So from this we will get one element whose order is equals to 6. So I will take A, and A be either 1, 2, 3, 4, 5 or 6. Then order of A is equal to 6. So we are going to find that any element in G such that order of A is equal to 6. So we see that order of 3 and it is equals to 6. That means 3 to the power 1 it is equals to 3, 3 to the power 2 it is equals to 9, and applying the operator multiplication module 7 it will be 2. That means 9 divided by 7 will get 2 as a remainder. Okay, so this is 2. 3 to the power 3 and it is equals to 6 after divided by 7 we will get 6 as a remainder. 3 to the power 4 will get 4 as a remainder. 3 to the power 5 will get 5 as a remainder, and 3 to the power 6, then from the above we will get the remainder 1, and 1 is the identity element. So G is a cyclic group and 3 is the generator. Okay, so the order of 3 is 6 and it is equals to the order of a group. So 3 is the generator, and therefore G composition, and the composition in the multiplication module 7 is a cyclic group. Okay, and 5 is also the generator of a cyclic group G composition. So where 5 to the power 6 is equals to 1, where 1 is the identity element. So 5 is also the generator, and 5 is relatively 6, so 5 is a generator. Applying the above theorem we will get it is also a generator. Okay, so I will take one more examples on the cyclic group. So here is the second example. So that the group G Z5 comma plus, that means the addition group of all integers module 5 is cyclic. Find all generators of Z5. So here is the solution of the examples. Here Z5 it is equals to 0, 1, 2, 3, 4. So there are 5 elements 0, 1, 2, 3 and 4. And now 0 into 1 it is equals to 0. 1 into 1 it is equals to 1, 2 into 1 it is equals to 1 plus 1, that is 2. Okay, with the third bracket. These are the congruent relation. Therefore, 3 into 1 it is equals to 3, 4 into 1 it is equals to 4, 5 into 1 is equals to 5, and 5 it is so this element are in Z5, so 5 is equal to 0 as well. This is the identity element. So thus order of 1 is equal to 5, so Z5 plus is a cyclic group and 1 is the generator. Okay, so since 5 is a prime, so all other generators of the above group, and they are 2, 3 and 4. Okay, so these are the generators of the cyclic group and Z5 plus, where 5 is prime to 1, 2, 3 and 4. Okay, so after that we'll take the third example, so that the group Q plus is not a cyclic group. So if possible, let Q plus be a cyclic group generated by an element A, and A is belongs to Q. Then A is not equals to 0, and every element of Q can be written as NA, where you know that plus is the operation. This is the binary operation. So every element of Q can be written as n of A for some n. Now 1 by 3 into A, it is belongs to Q, but 1 by 3 into A cannot be expressed as n into A. Okay, so for some integer n. So in that case, where plus is the binary operation, but 1 by 3 into A is belongs to Q, but it cannot be expressed as n into A. So for some integer n, so A is not a generator of Q plus. If A be a generator of Q plus, then it can be written as n into A. But in that case, 1 by 3 into A, it is the element of Q. Okay. So, but it cannot be expressed as n into A for some integer n. So hence A is not a generator of Q plus. Therefore, Q plus is not a cyclic group. So in that case, 1 by 3, that is the fractional number, is not a generator with respect to the operation addition. So Q plus is not a cyclic group. Now we are move on the next example. So here is the example. This is the fourth example on the cyclic group. If G is equal to generator of A is a cyclic group of order 40. So A to the power 40 is equal to E. Find all distinct element of the cyclic subgroup, A to the power 8 and A to the power 10. So A to the power 8 and A to the power 10 both are the generator. So we are going to find the elements of the generator A to the power 8 as well as A to the power 10. So here A to the power 8, the generator of A to the power 8, and it can be written as A to the power 8 whole to the power n such that n belongs to Z. So now order of A, it is equals to the order of a group. So G is the cyclic group, so there exists a generator A such that the order of A is equals to the order of a group. That means order of A is equal to 40. So A to the power 40 is equal to E, where E is the identity element. So therefore A to the power 8 whole to the power 5 and it is equals to E. So order of A to the power 8 and it is equals to 5. Okay. So here n is equal to 5. So therefore n is the order of A to the power 8. So A to the power 8 is a generator of the cyclic group G composition. Okay. So therefore order of A to the power 8 is equal to 5. So the elements of A to the power 8, and they are A to the power 8 whole to the power 0, A to the power 8 whole to the power 1, A to the power 8 whole to the power 2, A to the power 8 whole to the power 3, and A to the power 8 whole to the power 4. So there are 5 elements of the generator A to the power 8. And this is equals to E. So A to the power 0 is equal to E. A to the power 8 whole to the power 1 is equal to A to the power 8. A to the power 8 whole to the power 2 it is equals to A to the power 16. A to the power 8 whole to the power 3 is equal to A to the power 24. And A to the power 8 whole to the power 4 it is equals to A to the power 32. So the elements of the generator A to the power 8, and they are E, A to the power 8, A to the power 16, A to the power 24 and A to the power 32. There are 5 elements of a generator A to the power 8 of a cyclic group G composition of order 40. Similarly, we will find the elements of the generator A to the power 10 of a cyclic group whose order is 40. And you know that A to the power 10 whole to the power n, where n is belongs to z, that is equals to e say, and applying this one, that means order of a is equal to 40. So at a to the power 40 is equal to e, we will get a to the power 10 whole to the power 4 is equal to e. So that means order of a to the power 10 is equal to 4. Okay, so the generator a to the power 10 contain 4 elements, and they are a to the power 10 whole to the power 0, a to the power 10 whole to the power 1, a to the power 10 whole to the power 2, and a to the power 10 whole to the power 3. And after simplifying this, we will get the elements, and they are e, a to the power 10, a to the power 20, and a to the power 30. So the generator a to the power 10 contain 4 elements, and they are e, a to the power 10, a to the power 20, and a to the power 30. And after that, we will take the fifth example on cyclic group. So that the cyclic group of prime order has no proper non-trivial subgroup. The fifth example. So here is the solution. Let G composition be a finite cyclic group of prime order P, and let H be a subgroup of G. Then by Lagrange's theorem, the order of every subgroup is a divisor of the order of a group, and hence order of H is equal to 1 or order of H is equal to P, but P is a prime number. Thus, G can have no proper subgroup. This is the proof of the above examples or properties. So after that, we will take the sixth example on the cyclic group. Here is the example. So that the nth root of unity form a cyclic group under ordinary multiplication. So you know that nth root will take x is equal to 1 to the power 1 by n. That means x to the power n is equal to 1. So you know that x to the power n can be written as cos 0 plus I sin 0. Okay, and x to the power n is equal to 1. So 1 can be written as this. So cos 0 is equal to 1 and sin 0 is equal to 0. So this is equals to this one is the simplest form, that means the general form, cos 2k pi plus I sin 2k pi, where k is equal to 0 plus minus 1 plus minus 2 and up to infinity. So x to the power n can be written as cos 2k pi plus I sin 2k pi, where k is equal to 0 plus minus 1 plus minus 2. So therefore x is equal to cos 2k pi plus I sin 2k pi whole to the power 1 by n, where k is equal to 0, 1, 2 and up to n minus 1. So in that case, where k is equal to this. Okay. And after applying the de Moivre's theorem, then from the right side we will get x is equal to cos of 2k pi by n plus I sin 2k pi by n, where k is equal to 0, 1, 2 up to n minus 1. And this is equals to, you know, that e to the power 2k pi I by n. So thus the set G of nth root of unity is given by, so there are n number of roots, and they are 1. The first one is 1. When if we put k is equal to 0, we get 1. When we put k is equal to 1, we get e to the power 2 pi I by n. When we put n is equal to 2, we get e to the power 4 pi I by n, and up to e to the power n minus 1 pi I by n. Okay, there are n distinct root of x to the power n. Okay, and we will take omega is equal to e to the power 2 pi I by n. So from this we will get 1 omega square and up to omega to the power n minus 1. These are the root of the nth power of x. From this, first we shall show that G form a group under multiplication. So it is obvious that Z1, Z2 belongs to G. So this implies Z1 into Z2 belongs to G. So G is closed with respect to the operation multiplication. As well as multiplication is associative on the set of complex numbers C, and G is a subset of C, so multiplication is associative on G as well. Okay, and 1 is belongs to G, and 1 dot Z is equal to Z dot 1 is equal to Z for all Z belongs to G. So 1 is the identity element. Okay, and 1 is lies in G, so identity element is exist and it is belongs to G. And if omega to the power p is belongs to G, and 1 less than equal to p less than equal to n, then omega to the power n minus p is also belongs to G. And omega to the power n minus p into omega to the power p, it is equals to omega to the power p into omega to the power n minus p. That means omega to the power n, it is equals to 1. So omega is actually the nth root of the unity. So this one is equal to 1. So omega to the power n minus p, it is the inverse of omega to the power p. So hence G composition is a group. So G composition satisfy all the four properties of the group theory. That means closure, associative, identity, and inverse property. So G composition is a group. Again, all elements of G are integral power of omega, and omega to the power n is equal to 1. So hence omega, that means e to the power 2 pi I by n, is a generator of order n. So this is the solution of the above examples. So I'll stop here. Thank you.